Welcome to my talk, Digital Twins for Sustainable Fertilization. My name is Heike Bach. I'm director of the company Vista. We are offering integrated solutions for managing the water, energy, food nexus. Part of these solutions are smart farming services that we offer to farmers. These are combined in our portfolio of Talking Fields. With Talking Fields, we support the farmer with his smart farming decisions along the growing year, starting from the greening management to improved soil sampling, but we also do site-specific seeding, fertilization, crop protection, irrigation and harvest. We do this on 4 continents and for hundreds of thousands of hectares. Our partner with this is the Next Farming platform, which allows us to give the prescription maps to the machinery. But today I don't want to talk about Talking Fields, but on the new solutions that we have to offer connected to fertilization. The concept that we are using here is a digital twin concept, so a replica of a living or non-living physical entity. So bridging the physical and the virtual world. For us, it's a field that we want to create a digital twin from. By integrating our knowledge from data-driven analytics as well as other physical knowledge, and we make strong use here of satellite data. The simulations tools that we use for the digital twin are radiative transfer modeling and the land surface process model PROMIT that we developed. How does it work then? With these two tools, we are simulating a digital twin model of an agricultural landscape as shown here. On the left side, you see a simulated virtual satellite image. On the right side, you see the one that is really observed by the satellite. We can go through the growing cycle with these simulations and see how good they match together. Starting again from March, moving over to April, May, and so on. Input to these simulated scenes are topography, soil meteorology, crop phenology and physiology, knowing about the typical leaf area development of the crops and simulating its growth with the crop growth model and meteorological conditions. So you can say we extract and use textual information from the satellite image on, for example, crop type, phenology, biomass, maturity, and so on, and combine it with heterogeneous temporal dynamics through the PROMIT model. And with this, we can construct and simulate each Earth observation sensor acquisition. So it's a different procedure to use satellite data. And if we do this, we can now use it for fertilization as well. You can see here maps, textual maps that we generated from satellite scenes, like the leaf area, leaf chlorophyll, how much nitrogen was taken up by the complete crop, and for example also the soil organic content as retrieved from satellite images. This is then combined with meteorological data, soil and vegetation information in the PROMIT model that we can generate it from this really temporal dynamics of the leaf area every day. We can simulate the fertilization that the farmer would give, the mineralization of the soil, how much yield is produced and how much protein is in the yield. That is here an example of wheat. So the whole chain of fertilization down to yield and protein content can be simulated with this tool. And this is then used for decision support as shown here. So we simulate every day the variables of textual information as described before. Depending on the fertilizer applied, we simulate the soil nitrogen at different levels here, just shown 4 of these textual layers that we have. But these can now be used that we say, okay, let's do this simulation with different fertilization scenarios. We start with a scenario with low nitrogen application, and scenario 5 is the one with the highest nitrogen application. And from this we can simulate for this field how this field reacts on yield, depending on increased nitrogen input, protein content. You see is increase, of course, with increased fertilization, but you also see that the nitrogen leaching to the groundwater goes up. And so we will, from this analysis, we can define an optimum where we still have high yields, but the nitrogen leaching to groundwater is minimal. or is smallest. So this optimum can then simulated and extracted for each of the 10 by 10 meter pixels, so we can make an application recommendation based on this digital twin concept. You can do this also on a larger scale, not only on a field scale, like shown here for a drink water preservation area, where we can simulate for all the crops that are grown there the nitrogen input, the typical fertilization according to present law, and here the outputs, how much is taken up by the crops, how much is going to the air, and how much is leaching to the groundwater. And on the right side, you see the balance between input and output. And the good thing with this is that you now can integrate it over the whole drink water area, and you can see here during the growing cycle how the different compartments develop. So you see the increased fertilization amount in total. There you see how much nitrogen is taken up by the crops, so really extracted from the soil. And also importantly, you see the nitrogen leaching to groundwater, which is very low during the whole summer, but in the winter season in the region here, where we have no catch crops, we see that in the winter months nitrogen leaching occurs. And now we can use different scenarios, reduce, for example, the amount of fertilization to 80% because we are in a region where we have reduced fertilization, or we can introduce catch crops and see the impact of this on the whole system. That is now possible with the digital twin concept. As a short conclusion, we believe that digital twins using satellite observations and simulations can guide agriculture on its path to sustainability. So our goal is to achieve 100% efficient use of nitrogen fertilization, that we really get the best for economy and environment. And we believe that the digital twins can offer real decision support to the farmers, and with this help to solve the conflict between agriculture and environment. Thank you very much for listening.